Hi viewers, welcome back to our channel. It's your host Abdurrahim Babatunde Bukola. I am here today on another exclusive version of a video tutorial on Nobel preset designers. Today I am going to be explaining and tutoring you guys on how to set up an air separation rigorous simulation with Aspen Adsorption software. Aspen Adsorption software is a software like Aspen Custom Modeler. Is also part of the Aspen 1 suite. So it is used for rigorous modeling of adsorption tower, separation tower. So you can model the system because we don't really have it in Aspen Plus, like a rigorous modeling of adsorption tower. So you can use the customized features of Aspen Adsorption for rigorous modeling of adsorption tower and absorption system, like a CO2 carbon capture system, like air separation that we are doing for oxygen adsorption, and different kind of adsorption system can be modeled with Aspen Adsorption code. So, and today I'll be demonstrating adsorption cycle. I'll be demonstrating two steps, which is the adsorption step and the is a pressure swing adsorption system. So when the pressure is high, that will be absorption process where oxygen is absorbed into the zeolite adsorbent bed, and then there is a depressurization stage where there will be desorption of oxygen and purging of oxygen from the system. So in order to use this simulation code, it follows like Aspen Plus 2. You first need to declare the component to use. So we have two components in our system, the nitrogen and oxygen component. So, and you go to simulation area in order to declare the component and click on configure property. So you can use a custom properties, or you can decide not to use the property, like if you are, because this is actually like the software is based on Aspen Custom Modeler. You understand? So you is basically, if you know how to use Aspen Custom Modeler, you can use the software. So so I'm going to use a property system from Aspen Properties. So in order to create a new one, you can use the one that you have before by using the edit property definition 5, or the one that you have by using use property definition 5, or import another one to the simulation. So this one, I'm going to create a new one by clicking on edit properties. Aspen property is just like Aspen Plus property environment. You can see it's only having property environment. So here we are going to declare the component. So I'm going to write N2 here. Going to, okay, find then O2, which stands for oxygen. Then I'm going to use pengrobinsin as my equation of state to calculate the property of the chemical system. So you have pengrobinsin equation of states. Then I'm going to run the property analysis. Now to make sure there is no error in the property file. Okay, we have results, so it is working fine. So I'm going to save it. Then I'm going to close, save it. Then I'm going to close, so I can go to this file. So then I'm going to, it has been configured with embedded Aspen property. So then I can use the components in the Aspen adsorption environment. So you can see more about the system here, the pengrobinsin and all these properties. This one are the default system steam, for water, and all these kind of things. So we have a point graving that has been added. So I've configured the properties. So the next thing is the flow sheet. So this is the flow sheet. So you can choose some custom model like the adsorption model that we have in the setting up the flow sheet, because that's the next thing to do. So I'm going to set up the flow sheet by using a feed where's the feed? Okay, a gas feed for my air feed. Then I have a two valves by using the gas valve here. Then I have another valve here for the oxygen product. Then another valve on the top. Then I'm going to use a gas product for the product's boundary stream, and for the hydrogen another gas product. Then we have the bed, the gas bed in between them over here. So the gas bed has been set up. So I want to rename the component. So I'll be renaming the component one by one. So this I'll call feed. These I'll call feed valve. These I'll call oxygen product valve. And these I'll call oxygen O2 product. These I'll call nitrogen product valve, NPV. These I'll call N2 product. So the next thing is to pick material stream. So I'm going to go to stream type. So you have gas material connection. We connect source to this. You can also pick it from here in more default. Oh, I need to add a gas tank. So I need to add a gas tank void to the add one here, and I add the other one. It's basically just an icon. So basically just an icon or something. I can rotate or add. For example, let me just change this icon and rotate it up and down. So then I'll add the material connection just to be sure. So, and this is going to this. Okay. Then add another material connection. The material connection. So for the oxygen stream after the depressurization, and add the product here. So after setting up the Let's give this one the name top tank. The name top tank. This is our bed. So I'm going to call this bed, and I'm going to call this top tank. Okay. This is the bottom tank. Bottom tank. While this is the top tank. Top tank. So we have set up the flow sheet. The next thing is to configure the unit operation in the flow sheet. So we'll configure the stream first. So for the stream, you go to double click on it, you are going to see the configure block or stream. Then you have different model type. This is a reversible pressure setter for a valve that is reversible flow, that can be backward flow, forward flow, and the pressure between the inlet and the outlet determine the flow of the system. So we have a non-reversible one, you understand. So, and we have the true for reporting the value. So in this place, we are going to specify the forward composition and the flow rate. So this is free, so leave this one as free. So because you can only specify one variable, you understand, because there is something that you call degree of freedom, because the dynamic solver, so you must specify some specific variable and leave some as free, so that when the calculation is done, it's basically the flow of a system depends on the pressure. So most time we used to fix the boundary pressure. So when there is pressure gradients, that will be flow through the system. So for the inlet to the source to the flow sheet, it is air, so that's 0.79 nitrogen and 0.21 oxygen. So for the pressure, I kept it at 0.045 bar. So it has the pressure for the inlet to the system. So then we are going to check the one for nitrogen. So this one, you specify the backward flow, that is the reverse flow. So what will be the system? So the pressure is very, very important. So that's the downstream pressure that the flow is going to depend on. That's atmospheric pressure 0.13. So you can leave the composition, but although let's just put this one to be 1. So that will be logically right. So but it's not going to get to a backward flow unless we allow it to get to a backward flow. So then we do that for the oxygen product stream. So for the oxygen, we have 0, we have 1, and 1.013. But the pressure is very, very important, and temperature. So that's the specification of the feed and the product. Then we specify the valve. So for the valve is basically we can leave the valve for now. So the meaning of the valve is like we have a reversible pressure flow like that of the stream 2. So the flow depend on the pressure in between inlet and outlet pressure, and it can be based on non-reversible, which is like if you want to model a check valve, then you have a non-reversible delay. If there is a delay in the inlet to before you understand delay system. So the characteristics, you can put linear, ISA type, choke flow, pop flow. So you have the specification required. If you want to be using CV for the specification, or you want to be specifying the flow of the system. So we can use this type of active specification. If it is 2, that means it is using CV for the specification. So this is the CV of the flow. Then this, if you choose 3, that is using flow rate for the specification. So for energy balance, you allow you to calculate energy balance type. So before we leave that the valve system, because we are going to use a tool to specify the parameters of the valve as simulation is running. So I have to do the bed specification. So for the bed specification is like an adsorption bed. You can have multiple layer of adsorption. You can have different type. For example, we are having one layer now. So if you have multiple layer, there will be multiple section of the bed that you can fully configure into your own, into the way it's supposed to be. Then you have different orientation too, or different, we have horizontal bed, radial bed, or user defined. So you have a dimension for this for the layer nodes. So if you want it to be one dimension or two dimension, if you want to use heat exchanger inside the configuration of the bed, you can put it there and you specify the parameters of the heat exchanger. So these are the bed. So in order to use this bed, is either you click on this layer or you click on configure the first layer. So in order to specify the layer parameters, so I have you can save the assuming when you have done the layer configuration, you can save it and use it in another subsequent model. So but I have a model that I'm going to use, so and I'll explain the specification after using the model. So is this model 2. So it's going to configure the new model based on the model 2, that layer that I've saved. So it has done that. So this is the specification of the model. You have the general model, the partial differential equation, and then the depressurization. You can use this type. So you have different type that is there, which, so we are using this type. So the numbers of nodes is numbers of points that you want to keep record. You can make it to be 50, you can make it 20. The greater the numbers of good, the greater the accuracy of the model. Then you have the material momentum balance. So material balance calculation should be conversion only. So that should just be conversion of material. So then we have the momentum balance assumption is based on Eigen equation. Then you have the kinetic model, solid, lumped resistance, linear, constant. So that's the kinetic model. It should be based on lump. So you have multiple options that you can choose from. And if you are confused about the option, you can use the help here, which will show you the equation model. So you can set the parameter correctly in the specification page. So this is the help that you can use to get all those parameters, like the information about those parameters. So and the method that you are using. So then we have the isotherm. So we are using friendly one. So and you have multiple here. Then the isotherm dependency, like the driving force of the isotherm. So they based on the partial pressure. Then we have the energy balance, no isothermal with no condensation. The heat absorption is constant. Heat transfer coefficient is constant. Then you have the heat transfer. There's no heat transfer to the environment. So then you have solid phase heat capacity. So and there's no reaction in the model. So the procedure is so in order to check the specification of the parameters. So this is the specification. The height of absorption layer is 2 meters. The diameter is just 0.5. Then we have the voidage 0.4. The interparticle voidage is very small. The density of the bulk solid and the constant mass transfer coefficient is the same. The isotherm parameter is depend on the isotherm model that you chose. So you can see the configuration. This is a vector. So this is just the first parameter that has been specified. The second parameter is not specified. Then you have the heat of absorption. The heat of absorption is given, and the specific surface area of the adsorbent is also given. So that's it. So that's the specification. So in order to initialize the column, that is what will be in the initial value for the variables, like the composition variables, the pressure, like for example, the major thing that is very important is like what is inside the system, what will be the initial composition of the system. So we are going to use nitrogen to be like the system just contain nitrogen. So that's the initial composition. Then after you have specified the initial composition, because you have multiple nodes, this just you specify for just the first node, then you can initialize to the remaining node by clicking on this button. So you want to copy, you can see set the value to equal to the first node. So it's going to do that for the remaining node. Okay, so after it has done that for the remaining node in the layer, you can close this, and then you do that for the bottom tank and the top tank. To what you have done, initialize the composition of inside the hold up composition inside the system, because it's actually a pressure setter. So you do that for this tank too. So you don't need to specify, it's all the volume, but you don't need to specify that now. So that's the default is correct, is enough. So for this, make this one to be nitrogen 0. So I can initialize the composition for the top tank too. So then basically nitrogen. Okay, so after we have set this up, we can initialize the run with a initialization run. So before I initialize it, I'm going to save it as a new file. So I've saved it, so I can run it like this. So the run is good, initialization is done. So, and I'll be creating some forms like the breakthrough curve, all those kind of things, before I started creating running in dynamics. So I'm going to create some form by clicking on add form over here. So I'm going to call it breakthrough curve. So this is my breakthrough curve. On the breakthrough curve, it's going to contain the product composition of the nitrogen and oxygen. The nitrogen and oxygen going to contain the product composition of nitrogen and oxygen in the nitrogen product and the oxygen product. So as you have it like this, I can change the color so as to make it correct. So I'm making one black. Okay, I'm making this one deep blue. Oh, let me look for a more deeper blue. I think it's glaring now. So then I'll create another curve to call the loading curve, solid loading, inside the belt. So for the solid loading inside the belt, I'm going to go to results. Okay, okay. So I'm going to check for the results here inside the layer. So for the solid loading, so the first two here, I'm going to copy it here. Then into the midpoint too, I'm going to copy it here. Okay, and the last point, I'm going to copy it here. So that's for the solid loading. And the last one is flow curve. Flow flow curve. For the flow, is going to be flow of feed result. Going to be flow of feed, nitrogen products, and oxygen product. Okay, nitrogen product and oxygen product. So for this, I can change the on value there too, so the color can be different. So after doing that, I'm going to create some kind of tool in order to do the cycle. So that tool is what we call the cycle organizer. So I'm going to create it. So I've created the cycle organizer. So in the cycle organizer, you can specify different steps in the cycle. So this is my first step. It's going to be based on 60 seconds of the simulation time. So you can make it to be event driven based on a particular variable in the flow sheet getting to a value, or maybe something change in a particular value that you set become a certain value, a expression become a certain value, you understand, or it's greater than a certain value. It's just a logical expression that you can make it. You can also make it to be dependent on the step that you have done. Maybe when a step has completed, you should do this step, you understand. So this is how to do the control of this step. So then after setting up the control of the step, the next thing is to do the manipulation that you want to do in the flow sheet. So this is the manipulated variable. So you can add variable by clicking on add over here. So I'm going to be adding feed valve because I want to close I want to make feed valve to be active in this case. So I'm going to make it to be 1 in the first step. So I'm going to add another variable, nitrogen product type, the active specification. Don't worry, I'm going to change everything. And I'm going to add the nitrogen product valve, the flow rate of nitrogen that will be coming, and I'm going to add the oxygen product valve active specification. So this is going to be equal to 1. This is going to be equal to 3 because I want to specify the feed valve here to be fully on, while this will be nitrogen product valve will be based on flow rates that I'm going to specify. The flow rate is 5.2 e raised to power minus 9. Then this will be equal to 0, fully close the oxygen product valve. That's for the first step. Then I'm going to add another step, which will be after. Yeah, it's going to be based on the data. So I can easily adjust this. So this is going to be 0. I'm going to fully close the feed valve in the second step and fully close the nitrogen product valve in the second step. After fully, if I don't need to add this, it's redundant. So then in the oxygen valve, I'm going to make it to be equal to 2. That is fully open based on CV. Then I'm going to add the variable for the CV value because I'm going to specify a CV value for it. It's not going to be based on 100. It's going to be 6 e raised to power minus. It's going to be very small CV. So you have to control the flow so that the flow will not leave the system, make everything dry. So this is the CV that is going to be. So then I need to specify the control for the cycle 2 to be equal to, because this is 40, this will be 40 seconds. So after doing this, you either click on generate cycle here in order to generate the code for the cycle that you have just set up. So you click on this place to generate the tags for the cycle. So it is generating. Okay, so it is done. After generating the tags, so you can close it, and the cycle has been generated and the simulation has been initialized. You can initialize it again in order to check the run if it is working fine. So now we have to configure multiple cycles. So I'm going to generate 25 cycle. So you go to cycle option to know the settings for the cycle. So the initial frequency, control, nonce. At the end of each cycle, you can take snapshots, that is, store the simulation result so that you can rerun the simulation from there, from the results. So I'm going to generate 25 cycle because the time for each cycle is too small, is just small. So it's going to do 25 cycle and stop the simulation after 25 cycle. So a different way you can. This one is for run control. Okay, since you have set up the, you don't need to check the run control again. Since you have set up the cycle, so you don't need to control the timing for the simulation again. Okay, so after everything has been set up, you can run the dynamic simulation and check the response to the cycle. So simulation is running, so it is running now. Okay, the simulation has completed the cycle, and you can check the message. Can check the time, 2500 seconds. So you can check our curve. So for example, let's check our BT curve. So you can see the curve of the flow rate of nitrogen, oxygen. Can show the value here. This is for nitrogen products. It is pure nitrogen, entirely pure nitrogen. And we have oxygen coming out of the purge stream. Okay, we can create another plot for the pressure profile. So let's create another form for the pressure profile. Let's call it pressure P curve. Let's call it pressure curve. So I'm going to be plotting the pressure of top tank and bottom pressure. Top tank and bottom tank. Pressure of top tank and bottom tank. Signify the pressure in the system. So it's basically the same pressure. So that's, we need to configure this to be 0 and this to be 100. So this is the profile as the pressure is coming in and coming down, and you can check the flow curve. Okay, Let's make this one to be 0 first. So this is for the first stage of nitrogen that is being produced, pure nitrogen that is being produced. Then this for the purging stage, and you have the purging stage, the adsorption stage for pure nitrogen, the purging state, the adsorption state, the purging state, the absorption stage. So the next thing we have to check is the solid loading curve. This for the solid loading, we have 0 and 100. So you can zoom in to see clearly here the solid loading for each state. So you have different color for the bed layer, how the solid increase, decrease. This be mostly for the purging states, where you have the solid loading being decreased. And so this is when you have the adsorption. So you can see for most of the system, for especially hydrogen or something, or you can see it as a plot here. So you have oxygen in the bed. This is for the starting point, and you have oxygen here too. You have oxygen here too for the starting point using this same kind of cycle. So you have oxygen E16, E7. So since we have more of nitrogen in the system, that's why we have more nitrogen adsorption inside. So, and there will be some equilibrium point as time goes on. So we are to look for the cycle for the equilibrium point. So, and that's what we see in this place. Is the most important thing is actually the PT curve, where you have high hydrogen nitrogen production, and you are able to maintain the purity of the nitrogen production for the adsorption step. As you are sending oxygen in, you are able to maintain the purity. So that's the major thing about the system. So as we are able to explain how to do this kind of simulation with Aspen Adsorption software, I hope you're able to grasp the concept of the software and use it for your simulation, for your research, for your analysis. So if you have any question or you want to get this model, you can send me an email to our email address, or you send me a message on WhatsApp or Telegram. So I'll be glad to hear about your research and your projects, your simulation projects, your process engineering design, or if you have any topic that you want us to work on our channel, you can feel free to send me a message or email. So thank you very much for your time. Thank you for watching. So make sure that you share with among your friends and your colleague, and you share our channel, and you subscribe and hit the bell icon in order to get more exclusive, interactive, educative video from us. Thank you for your time. Is Abdurrahim Babatunde Kukola.